Swayam Prabha. Digital India. Educated India.
Right. So today we are going to discuss the decision modeling, the special cases in linear programming. There is a second lecture on this. That is the special cases in linear programming. Um, we know that there are four different special cases that we decided to discuss. The degeneracy, alternate optimal solution, infeasible solution space, and unbounded solution space. Now, degeneracy, which we have discussed in our last class, basically talks about degenerate solutions when some values are zeros in the basis. Now, variables become zeros in the basis. This happens when there is a tie in the leaving variable in the previous table. So when there is a tie, the two resources becomes bottleneck at the same time, and if any one of them is used to bring some variable in the basis, both gets exhausted. One goes to the non-basic, but the other remains in the basis with a zero value. Alternate optimal solutions occur when the profit line is parallel to one of the bounding constraint lines. So we know that the optimal solution is one of the basic feasible solution, and the basic feasible solutions are corner points of the solution space, and the corners are made by, the two corners are made by a straight line, which is a constraint line. Suppose that constraint line is the bounding constraint line, then what is going to happen when the profit line is parallel to that bounding constraint lines? Then the two basic feasible solutions will become optimal at the same time, which also means that every point which joins those two basic feasible solutions are also optimal. So we shall get infinite optimal solutions under those situations. The question is, yes, this can happen, but how to know when we are making use of the simplex procedure? The third case is the infeasible solution space. That means there is no solution space. Constraints are such that the solution space is not possible to have. So how to know this when we are making use of the simplex methodology? And the fourth one, where the solution space is unbounded. That means there is no bound to the solution space, particularly if we have a maximization problem, then we cannot solve because the infinite solutions will be resulted. For minimization, this may not be a problem because it is bounded on the lower side. So let us first take up the first one amongst them, that is the alternate optimal solution. So here is a typical linear programming problem which we shall make use of to explain the alternate optimal solution situation. Maximize z equal to 2x1 plus 4x2 subject to x1 plus 2x2 less than equal to 5, x1 plus x2 less than equal to 4, and both x1 and x2 are greater than equal to 0. That is the non-negativity criteria. So if we take the augmented problem, then we know that we need to add two slack variables, x3 and x4, and they should occur in only one equation so that they form an unity matrix between them, and all the equations are in canonical form. So that is exactly what is maintained. We have got now two equations, and the objective function also includes x3 and x4 with zero coefficients, and all of them should be non-negative. So these are the already satisfied, and we have the augmented problem. So we can now try to first see that the graphical solution. So x1 plus x2 equal to 4 and x1 plus 2x2 equal to 5. The two constraint lines are drawn, and since the original constraints are less than equal to, so they are in the origin side, and we get a solution space. The solution space is bounded by four different points, that is O, A, B, and C. Now look here, the bounding, one of the bounding constant line, that is x1 plus 2x2 equal to 5, is parallel to the objective function line, that is maximize z equal to 2x2 plus 4x2. Because x1 plus 2x2 and 2x1 plus 4x2 have the same gradient. So because of the same gradient, the two lines are parallel. That means the profit line before leaving the solution space, would be coincident with this particular what you call line, that is line segment AB. All right. So therefore, both A and B would be our optimal solution. So let us see that if we evaluate, point O is 0, point A, the objective function value 2x1 plus 4x2, 2 into 0 plus 4 into 5 by 2 equal to 10. Point B, 2 into 3 plus 4 into 1 also equal to 10. And point C, 2 into 4 plus 4 into 0, so equal to 8. So we see that the A and B both are optimal, and that means that the entire line segment that joins A and B are also going to be optimal, right? So not only A is optimal and the B is optimal, which are the two basic feasible solutions, but the entire line segment AB are also going to be optimal. So that means an in-between point like this point or this point, they also would be optimal. All right, so we have alternate optimal solutions in this particular problem. Now let us see how a simplex procedure would, what is going to happen if we use the simplex. So before we do that, here is the profit line, which is moving parallel to itself. So, initially it will be like this, and the solution space OABC, as the profit line moves at one point, it will be coincident. So point A is optimal, point B is also optimal. Hence the entire line from A to B represents infinite number of optimal solutions. Now, here is how to solve the problem by simplex. We have already seen the augmented problem previously. So here is the simplex first table. In the first table, x3 and x4, they are in the basis. And these are the values 5 and 4. X1 and x2 coefficients are here. The Cj values are 2 and 4 because this is the objective function. And the Ci values are 0 and 0 because these are resources, because they are the slack variables and they are associated with 0 coefficients in the objective function. So therefore the Zj would be 0 initially, and Cj minus Zj will be 2 minus 0 equal to 2, 4 minus 0 equal to 4, and obviously the variables in the basis, they must be zeros. So since 4 is the highest and it's a maximization problem, so x2 would enter the basis. So which is the bottleneck resource? X3 and x4, 5 by 2 and 4 by 1. So since 5 by 2 is less, that means x3 is becoming the bottleneck resource and x3 would be leaving the basis. So x3 is the leaving variable, x2 is the entering variable in the basis. That is the simplex first table. And in the second table, thereafter, if we compute, so this is the our key row and the intersecting element is 2. So if we divide all the elements by 2, then we have 5 by 2, 1 by 2, 2 by 2 equal to 1, 1 by 2, and 0 by 2 is 0. And other elements, so this value 4 would be 4 minus 5 into 1 by 2, that is 3 by 2, 1 minus 1 into 1 by 2, half. The key column should be in canonical form, so 1 and 0. And this 0 would be 0 minus 1 into 1 by 2, so minus half. And this 1, no change because there is a 0 here. So 1 minus 1 into 0 by 2, 1. And if you recompute the Cj minus Zj values, then this time the Zj equal to for x1 is 4 into half, that is 2, half into 0, so nothing. So 2, and Cj is also 2. So Cj minus Zj is 0. And here 0 minus 4 into half, that is minus 2. This is interesting. What is happening? Look here. This second table is optimal because it's a maximization problem and none of the Cj minus Zj value is positive. So definitely we can say this is an optimal solution, and that optimal solution is x1 equal to 0 because it is in non-basic, and x2 equal to 5 by 2. So z equal to 10. So this is the optimal solution as we have seen earlier in the graphical method. But very interesting thing is that all Cj minus Zj's are not negative. There is a 0. That means alternate solutions exist. So how to know that there is an alternate solution coming up? So there will be a 0 value in the Cj minus Zj. So if we get an optimal solution, but there is a 0 value in the Cj minus Zj value of the optimal table, then we know that alternate solution exists. That means there will be no improvement in the objective function value, but uh, we shall have another solution, and that another solution is a truly another solution. It's not degenerate, so that there is a same point and we get another solution which is basically the same. It is not like that. It is a distinctly different another solution, and it definitely returns another value. All right, so this is the difference between degeneracy. If we now try to get another the solution by bringing x1 into the basis, what we shall have is another solution which is a distinct from the current solution, that is x1 equal to 0 and x2 equal to 5 by 2. So let us see what it is. So x1 comes into the basis, and between 5 by 2 and half and 3 by 2 and half, 3 by 2 and half is the bottleneck. So x4 leaves the basis, x1 comes into the basis. So here is the next table. Here is the key row. So intersecting element is half. So divide everything by half. So this becomes 3, 1, 0, minus 1 and 2. And others will be used by rule, and key column would be for canonical form requirement will be 0 and 1. So this 5 by 2 minus 3 by 2 into half by half, so is 1. These 1 would remain 1 because it's in canonical form, and also there is a 0, and half minus half into minus half by half. So half plus half equal to 1, and 0 minus half into 1 by half, so minus 1. So once we get this, then again we find the Zj value. X1 and X2 are in the basis. So X3 would be 4 into 1 plus 2 into minus 1, that is 2. 2 is Zj, and Cj minus Zj will be minus 2. And in this case, minus 4 plus 4, Zj equal to 0. Cj is also 0. So Cj minus Zj is 0. So look here, once again, we have x4 to come into the basis. All right. So if now we bring x4 into the basis, so which one would be leaving? X1 would be leaving. So as if you then solve, you get back this original optimal solution. So then x4 would come into the basis once again, and x1 would leave. So this particular solution, that is 0 and 5 by 2, would return once again. So the two alternate solutions will keep moving from one another if you continue the simplex procedure. It's all right. So note that the 0 value in the Cj minus Zj for x4 in the third simplex table. This means the third simplex table is optimal. The corresponding solution is x1 equal to 3 and x2 equal to 1 and z equal to 10. However, since Cj minus Zj 4 is not negative, x4 will come into the basis. All right, and we can get back the original solution as we have discussed. So here is that simplex third to second table. technically we can again go from the third simplex table to the second simplex table. All right, so that what I said a few minutes earlier. What is happening here? We are alternating between the two optimal points A and B. This is because both A and B are in fact uh, all points on the straight line joining them are optimal, right? So that, whether all points joining them are optimal or not, that would not be returned by simplex. That we have to interpret because the profit line is parallel to the one of the bounding constant lines, of which A and B are two different points. Right. So once again, that if we summarize the observations on the alternate optimal solution, a 0 Cj minus Zj value in a simplex table with all the other Cj minus Zj values being negative in a maximization problem signifies alternate optimal solution. So the key here is a 0 Cj minus Zj value in the optimal simplex table. The next simplex table will also have a 0 Cj minus Zj value with all the other Cj minus Zj values being negative in a maximization problem. Both the tables will represent optimal solutions. It is possible to alternate between the two optimal solutions, not only the 2 points corresponding to the above mentioned tables, but all points on the straight line joining them are also optimal solutions. So whenever we have alternate optimal solutions, in a sense, particularly for linear programming problem, essentially we are going to get infinite number of optimal solutions. So this is about the alternate optimal solutions. I hope you have understood that there is a zero value in the Cj minus Zj, and although the solution is already optimal because none is positive, so if you consider that, you get back one of the older tables. You get back a new table which is alternate solution, and from there if you continue, you get back one of the older tables. Now let's come to the next problem, that is the infeasible solution space. So here is a problem: maximize z equal to 3x1 plus 2x2 subject to 2x1 plus x2 less than equal to 2 and 3x1 plus 4x2 greater than equal to 12, and both x1 and x2 are greater than equal to 0. So this problem, let us first try to solve graphically. So this is what happens, that 2x1 plus x2 equal to 2. So 2x1 plus x2 less than equal to 2 would be towards the origin. And 3x1 plus 4x2 equal to 12. So this is that straight line. And 3x1 plus 4x2 greater than equal to 12 will be on the other side of the origin. So what is happening, that we got no solution space because they are on two different sides. So this portion and this portion, although we need the common area, but there is no common area. So there is no solution space. The areas corresponding to the inequality constraints are on the different sides of the origin, and there is no overlap. So hence we have an infeasible solution space. So what is really happening here? If you look at this particular problem, then we see that these two constraints really, because one is less than equal to 2 and then is greater than equal to 12, but there is no overlap in the solution space. Just because one is less than equal to, another is greater than equal to, doesn't mean that there could still be overlap depending on the constant types. But in this particular case, there is no overlap, and that is why we did not get any overlapping area. And we can say that this problem doesn't have any solution space. So that is the case of infeasible solution space. So if we try to solve by simplex, let us see what happens. So because one constant is less than equal to, so we add a slack variable, that is x3, and the other constant is greater than equal to, so we need a surplus variable x4 and an artificial variable a1. This is an objective function is maximization. So therefore the artificial variable will be associated with a minus m, that is its profit coefficient, and both x3 and x4 will have 0 values. Now we know the artificial variable, the essential idea is that they have no physical significance. They are taken simply to bring the problem in a canonical form, so that initially x3 and a1 would be in the basis, and together they will form the unity matrix. X4 cannot form unity matrix because X4 is having a -1 coefficient. Even if you try to multiply that constant with -1, what we may get -3x1 -4x2 less than equal to -12. So in that case, we can manage with a positive x4, but we shall have a negative value which will create difficulty. So we added an artificial variable and with an infinite negative profit m, that means minus m. So with that we get the augmented problem. Now after we got the augmented problem, here is the simplex first table. X3 and A1 are in the basis, and the values are 2 and 12, and these are the coefficients. This x3 and a1 forms the unity matrix. X4 is with 0 and -1. So the question naturally comes that which is the entering variable and what are the Cj minus Zj values. Look here, the Ci's are not all zeros. So initially there will be Zj values and therefore Cj minus Zj values would be different from the usual. So how much it should be? Minus 3m, that is the Zj. So Cj minus Zj will be 3 plus 3m. And it is minus 4m. So Cj minus Zj will be 2 plus 4m. And for x4, it will be Zj is m. So Cj minus Zj will be 0 minus m. So minus m. Alright, so those values are calculated here. And since that 3 is too small, so therefore we have neglected that, and we get therefore Cj minus Zj is 3 minus of minus 3m, so that means plus 3m, so 3 plus 3m, and this one would be 2 plus 4m, so 2 we ignore and you can say it is 4m, and this one is minus m because Zj is m, so 0 minus m is minus m. Alright, so 4m is the highest, it's a maximization problem. So therefore x2 would be the entering variable. So which one should be the leaving variable? Look here, x3 is 2 minus 1, a1 is 12 by 4, so 3. So we naturally expect that initially that artificial variable must leave. But look here, something interesting is happening. The artificial variable is not leaving. Usually we expect that artificial variable should leave, because once the artificial variable leaves, then we get a problem where we have a feasible solution. But moment there is an artificial variable, it actually represents an infeasible solution, because if we cannot drive out the artificial variable, then we cannot solve the problem. So we have no option but to have x3 as the leaving variable, because x3 is the bottleneck resource. So x2 comes into the basis and x3 goes out of the basis. All right, so this is exactly what I said, that a1, the artificial variable, is not leaving the basis, it's not leaving. So let's say what then happens to the third table, right? You see in the third table, I think this at this point we get that the next table, that is your, yeah. So at this point x3 leaves the basis, and as x3 leaves the basis and x2 comes into the basis, so this intersecting element is 1. So we have 2, 2, 1, 1, 0, 0, and this 12 becomes 12 minus 2 into 4 by 1. So 4, this 3 becomes 3 minus 4 into 2 by 1 minus 5. This 4 is 0 because it's the key column. This 0 becomes minus 4. 0 minus 4 into 1 by 1. This minus 1 remains and this 1 remains. So this is how the table is, and this A1 remains, so minus M. So minus M into minus 5 plus M is Zj, and 3 minus 5M, so minus 5M. And here it is plus 4M, so 0 minus 4M, Zj is plus 4M. Cj minus Zj is 0 minus 4M, so minus 4M. And here it is 0 minus M, M is Zj minus M. So that means the optimal solution is obtained. The second table itself gives us the optimal solution. And if you really look into the optimal solution, very interesting thing can be found. What that is, that optimal solution is x1 equal to 0 and x2 equal to 2 and a1 equal to 4. So look, what is the meaning of the optimal solution with an artificial variable in the basis? That means, this is not feasible. It means that we got a solution which is infeasible, right? So if we get an infeasible solution, because once the optimal solution is obtained, we cannot solve it any further, and artificial variable remains in the basis, it means the problem has an infeasible solution space. Is it all right? So a problem will have infeasible solution space if we cannot drive out the artificial variable from the basis. All right. So this is exactly how to really find out that the problem has an infeasible solution space. An artificial variable in the basis of the optimal simplex table signifies an infeasible solution space. The fact that the artificial variable could not be driven out of the basis means the solution space does not exist. The problem needs to be terminated once we have an infeasible solution space. So this is the case, that is special case of linear programming, that is having an infeasible solution space. The infeasible solution space is returned when we have to take an artificial variable, but we cannot drive it out of the basis. So it remains in the basis, and it also becomes the part of the optimal simplex table, right? So in the optimal simplex table, we have an artificial variable in the basis. That means that solution space is infeasible. All right, so that's the second special case. Now let us go to the third special case, which is known as the unbounded solution space. Let us see what happens with an example. So here is an example: maximize z equal to 2x1 plus x2 subject to x1 minus x2 less than equal to 10 and 2x1 less than equal to 40 and x1 and x2 both are greater than equal to 0. So if we try to solve this particular problem graphically and try to see what kind of solution space we are getting, then that is what is represented here. So you see this line is 2x1 equal to 40. So this portion is the 2x1 less than equal to 40. And this line is x1 minus x2 equal to 10. And this side towards the origin side is the x1 minus x2 less than equal to 10. So these, this entire portion, because the axis is also there. So this is our solution space. Look here, these two lines, that means the x2 axis and these 2x1 equal to 40, they are parallel to itself. Since they are parallel, they are not going to meet. They are not going to meet, technically sometimes we say they will meet at infinity. So essentially it means that the solution space, that is OAB, is actually unbounded. So we have a problem here with an unbounded solution space. And if the problem is one of maximization, although there is a limit to the value of x2, but x1, but there is no limit to the value of x2. x2 can be as high as possible. Is it all right? So x2 can be as high as possible. x1 will be limited by 2x1 equal to 40. That means up to a value of 20. All right, so graphically we see that yes, here is a problem that has an unbounded solution space. Now let us see what exactly we can do about it. So try to solve by simplex, and if we try to solve by simplex, the first stage is to have an augmented problem. So here is the augmented problem. We add slack variable x3 and slack variable x4 in the two different constraints. So the augmented problem is maximize z equal to 2x1 plus x2 plus 0x3 plus 0x4 subject to x1 minus x2 plus x3 equal to 10, 2x1 plus x4 equal to 40, and x1, x2, x3, x4, they are all greater than equal to 0. So this is how we have our LP problem and we have our augmented problem, right? So after that, let us see the simplex fast table. So here is the simplex fast table. Basis is x3 and x4. The values are 10 and 40. Coefficient matrix is formed by x1, x2, x3, x4, of which the x3 and x4 are in the basis, so they form unity matrix. And x1 coefficients are 1 and 2, x2 coefficients are -1 and 0, and Cj values are 2 and 1 because that is the objective function, and 0 0 2 1 0 0, so that is written in Cj, and x3 x4 are in the basis, so their profit coefficients are written once again, that is 0 and 0. Since Cj's are Ci's are 0, so initial Zj is also 0, so Cj minus Zj, that is unit profit, net profit to bring 1 unit of x1 into the basis would be 2 minus 0 equal to 2, and for x2 1 minus 0 equal to 1. Since 2 is more, so x1 comes into the basis. And which one should be leaving? That 40 by 2 is 20 and 10 by 1 is 10. So x3 is the bottleneck. So x3 goes out of basis, x1 comes into the basis. Right? So that's the first task. And let us now try to get the next table. So this is the key row. Intersecting element is 1. So we reproduce the key row elements with x1 in the basis. 10, 1, minus 1, 1, 0. And the key column should be 1, 0 because x1 will be now having the in the basis. So that should be forming the unity matrix with x4. So 1, 0, 0, 1. Other elements 40, 40 minus 10 into 2 by 1, so 20. 0, 0 minus 2 into minus 1 by 1, so 2. 0, 0 minus 2 into 1 minus 2. So all the elements are obtained. Here that Ci will be 2. So therefore, the two variables, they are not in the basis, x2 and x3. If we compute, the Zj will be -2, and 1 minus of -2 is 3. So Cj minus Zj for x2 would be 3. And Cj minus Zj for x3 would be, 0 minus 2, so -2. All right, so then which variable should come into the basis? You can say that x2 would be now coming into the basis. All right, so variable that would come into the basis will be x2, and variable that would be leaving the basis. Which variable would leave the basis? Look here, if x2 comes into the basis, since the coefficient is -1, that means resource is not required, resource is actually released. That means, that cannot be the x1 cannot be bottleneck, right? Since here the 20 by 2, that is 10, so x4 would be then the bottleneck resource. So therefore x4, once again we have a minus value here, coefficient value. So for making 1 unit of x2, you require 2 units of x4 and -1 units of x2, x1 would be released. That means, sorry, and -1 units of x1 that will be required, which means 1 unit of x1 will be released if you bring 1 unit of x2 into the basis. Automatically, this means that x1 cannot be the bottleneck resource because Not only we do not require this resource to make x2, but we actually release it. All right, at a rate of 1 per unit. All right, so with that logic, we can say that therefore x2 comes into the basis and x4 goes out of the basis. So if x4 goes out of the basis, so obviously x4 leaves and x2 comes in. So this is the key row. The intersecting element is 2. So we divide everything by 2 and then get 10, 0, 1, minus 1 and half. Remaining elements we calculate, particularly key column from the canonical form point of view. So here is x1 and x2. So 1, 0, 0, 1, that form is maintained. And for the other variables, we use the formula. The formula is 10 minus 20 into minus 1 by 2. So it is 20, right? 20 into minus 1 by 2 is actually equal to 10 minus 10, and minus of minus 10 is plus, so it is 20. And this 1 will remain 1 because of this 0. And this 1 would be 1 minus 2 into 1 by 2. All right, so that means it becomes 0. And this 0 would become 2 because 0 plus 1 into 1 by this thing, the value. So I think this may not be 2, but this will be some other value. 1 into, it will be minus, it will be half actually. All right. So therefore, we get this particular table. And again, if you compute the Cj minus Zj, then we see that one of them is positive. So if one of them is positive, then we can get the next table. And then in the next table, we find that, we have an infinite value now coming in. All right. So this x3 gets into the basis and x1 gets out of the basis. So what is the value of 20 by 0? So you see an infinite value, a division of 0 is coming. And this also 10 into 20 minus 1 by 0. What does it mean? So you see what we are having basically, we are having a situation where we have infinite value in the basis. These two we calculated, that should be half. All right, so but then that doesn't matter because after all these really comes into the basis. So we have the infinity value coming into the basis. All right. So the variable in the basis assume infinite values in the fourth table. This means the problem does not have a finite solution. It also means that the solution space is unbounded. Right? So what really happens is that we come to a point where we have a bottleneck resource. There is a 0 and there is a minus 1, and minus 1 is a releasing resource, so cannot be bottleneck. So we have to take something, even 0 also, that resource is not required. So essentially we have no leaving variable. But by force, if you say that, okay, let's the x1 leaves, then an infinite value comes into the basis. Is all right? So the variable in the basis assume infinite values in the fourth table. This means the problem does not have finite solution. It also means that the solution space is unbounded. All right. So observation on the unbounded solution space is such that at some simplex table, the variable in the basis assume infinite values. The simplex algorithm does not terminate. This means the problem does not have a finite solution. It also means that the solution space is unbounded. So what is really happening in an unbounded solution space? There is a solution space, but there is no upper bound. Since there is no upper bound in a maximization problem, we might have an infinite value in the basis. So when you have infinite value in the basis, it is impossible to continue any further. And we can find a situation where the simplex algorithm does not terminate. Right? So this means the problem does not have a finite solution. It also means that solution space is unbounded. Now, before we go to the revision of the byproduct problem, let us give a quick summary of all the four cases that we have taken up. Right, so we'll go back to the initial slides. So we have the special cases in linear programming, and continuing with yesterday, we have taken four different cases. The first case is degeneracy. Degeneracy occurs when there is a tie in the living variable, although the degeneracy means a zero value in the basis. It happens when more than two constant lines goes through the same point, so that more than one basic feasible solutions, usually three or six, and in that way, when three constant line goes through the same point, six basic feasible solutions merge. All right, so when that happens, we have a zero value in the basis, and in a simplex table, it is known by, when there is a tie in the living variable. So those are called degenerate solutions. Degeneracy can create cyclicality, and that to break cyclicality, we have the Bland's rule. Take the leftmost variable or the variable with the smallest index. And other problem is that it slows down the algorithm. Today we have seen the alternate optimal solution when the profit line is parallel to one of the bounding constant lines. This is to be expected when there is a zero value in the Cj minus Zj of the final table. Right. So if you take that particular variable into the basis, we get another solution, a distinct solution. It's not that the same solution in another form. No, it's another point. So we get another point, and basically two sides of the bounding constant line. And when that is optimal, that means all points joining these 2 points, two optimal points are also optimal. All right, in a simplex, it is known by Cj minus Zj equal to 0. And in the alternate optimal solution also, the Cj minus Zj value will be 0. Then we have infeasible solution space. There is no solution space because the constraints are such. When that happens, we have a situation that there will be an artificial variable required, and we shall not be possible, or it will not be possible to throw the artificial variable out of the basis. It remains in the basis, right? So when the artificial variable remains in the basis, it cannot be thrown out of the basis. We should say that yes, it's a case of infeasible solution space. The fourth situation is an unbounded solution space. Solution space is not bounded. We cannot solve a maximization problem with this kind of solution space. So what happens here? An infinite solution comes into the basis, right? Because the solution space is unbounded, the simplex algorithm does not terminate. We keep solving the problem and we get infinite solution into the basis. All right, so these are the four different cases that we have discussed in these two lectures, yesterday, last class and today. So now let us see in the remaining time, a typical case of the byproduct problem. So we have already seen this byproduct problem. I have discussed how to make a simplex formulation, but graphically, does it give any further insight into this problem? So in a chemical process, two products A and B are produced. Both products need two operations for the production. A requires 2 units of raw material in operation 1 and 3, and uh, operation 1 and 3 units in operation 2 per unit. B requires 3 and 4 units in operation 1 and 2, and total raw material available is 16 and 24 in the two operations. Now, every time B is produced, a byproduct C is produced 2 times the volume of B. But only 5 units of this byproduct is profitable. So if produced beyond 5 units, it has to be destroyed at a cost of ₹2 per unit. So we are trying to solve this problem graphically. Profit coefficients are 4, 10, and 3 for A, B, and C. And we have to solve it for maximization of profits. So here is the, we have the 4 different variables. x1, x2, x3, x4, and x1 is product A, product B is x2, profitable part of C is x3, and destructive part of byproduct is x4. So the formulation came to like this: maximize z equal to 4x1 plus 10x2 plus 3x3 minus 2x4, and subject to 2x1 plus 3x2 less than equal to 16 and 3x1 plus 4x2 less than equal to 24, that in two operations raw material constant, and 2 times of x2 is equal to the profitable part and the destructive part. So 2x2 equal to x3 plus x4, that is the byproduct, and x3 should be less than equal to 5. An additional constraint, if x3 is less than equal to 5, because when x3 is less than equal to 5, x3 equal to 2x2. So that means when 2x2 is less than equal to 5, then x4 should be 0. So problem is how to make use of this nonlinear constant, because it's a nonlinear constant that makes the problem difficult, and x1, x2, x3, x4 they are greater than equal to 0. So this formulation part we had already discussed earlier. We had also discussed how to express this problem. The first table of the simplex also we have seen. In simplex, the nature of the problem is such that we can actually ignore this x4 equal to 0 if 2x2 less than equal to 5 constraint, and we can solve it by simplex. But anyhow, let us try to solve it graphically and see how to make it a two variable problem. So what we do, can we divide the problem into two parts? And if so, what are the two parts? If you think logically, then you find these two parts could be 2x2 less than equal to 5 and 2x2 greater than equal to 5, because those are the two different situations under which this byproduct problem can be really solved. So this is how exactly we do. In the first part, 2x2 is less than equal to 5, hence there is no byproduct. I mean, it's not that there is no byproduct, there is no destructive part of byproduct. So there is a destructive part of byproduct is not there. So x4 equal to 0, that means destructive part vanishes, and the profitable part x3 becomes 2x2. Is it all right? And in the second part, when 2x2 is greater than equal to 5, there is a destructive part of byproduct also. But x3 equal to 5, because 2x2 is greater than equal to 5. So x3 is exactly equal to 5, and x4 would be then 2x2 minus 5. So what we have done, we have been able to divide the problem into two parts. And in these two parts, in each of the part, there are only two variables. All right. Once again, when 2x2 is less than equal to 5, there is no destructive part of the byproduct. So x4 equal to 0 and x3 2x2. And when 2x2 is greater than equal to 5, there is a destructive part of the byproduct, but x3 will be 5 because that is the maximum number of profitable units, and rest would be x4, that is 2x2 minus 5, because x3 plus x4 equal to 2x2. So therefore, the original problem, which was of this form, in the new formulation, x1, x2, x3, x4, and in the first part, when 2x2 is less than equal to 5, then x4 equal to 0 and x3 equal to 2x2. And in the second part, when 2x2 is greater than equal to 5, then x3 equal to 5 and x4 equal to 2x2 minus 5. All right, so then we can express the two parts. In the first part of the problem, 2x2 less than equal to 5, x4 equal to 0, and x3 is equal to 2x2. So what we can do, this 3x3 then become, 6x3. All right, so 4x1 plus 10x2 plus 3 into 2x2, and x4 equal to 0. So we ignore this minus 2x4 term. So it becomes 4x1 plus 16x2, because this is 10x2, this is 6x2, together 16x2. And subject to these constants are not required anymore, then simply 2x1 plus 3x2 less than equal to 16, and 3x1 plus 4x2 less than equal to 24 and x1, x2 greater than equal to 0. And in the second part, when 2x2 is greater than equal to 5, x3 equal to 5 and x4 equal to 2x2 minus 5. So what we have, 4x1 plus 10x2 plus 3 into 5 minus 2 into 2x2 minus 5. So simplifying, this will be minus 2x2 minus 4x2. So 10x2 minus 4x2 plus 6x2. Here it is 15 and here is minus of minus 10. So plus 10. So 15 plus 10, 25. So in the second part, objective function is 4x1 plus 6x2 plus 25 and subject to the same constraints. So 2x1 plus 3x2 less than equal to 16 and 3x1 plus 4x2 less than equal to 24 and x1 and x2 both are greater than equal to 0. So this is how the two problems are there in the first part and in the second part, right? So when you try to solve it graphically, so this is how the graphically it will look like, right? The first part of the problem, when 2x2 is less than equal to 5. So this line is 2x2 equal to 5. So in the lower portion, this hatched area actually represents the 2x2 less than equal to 5. So objective function maximize z equal to 4x1 plus 16x2. So the solution space will be OACD. So you see these are the two constraints. Look, interesting thing, they are going through the same point. So if you take the axis, that is the x1 axis, which is x2 equal to 0. So x2 equal to 0, 2x1, these all the three constants are going through the same point. That means there is a degeneracy here. So, you must also observe those things. And another very interesting thing you observe that in the second part, where the objective function is 4x1 plus 6x2 plus 25, second part, that is the upper portion, when 2x2 is greater than equal to 5, these 4x1 plus 6x2 is actually parallel to 2x1 plus 3x2. So we are then going to have an alternate optimal solution. So look, very interesting problem that one part of the problem has a degenerate point and another part of the problem has an alternate optimal solution. So both are there. All right, so this is how the two solution spaces and the graphical solutions are going to be looking like. Now let us say the first part of the problem, that is 2x2 less than equal to 5. So OACD, that is the optimal solution, and the optimal solution comes out to be C. That is the optimal point, that is 17 by 4 by and 5 by 2 and z star equal to 57. All right, so that is what is the optimal point. This point C, that is coming from the first part of the problem. Although D is a degenerate point, but that degeneracy is not affecting us because this is a temporary degeneracy. All right, if you would have tried to solve by simplex, then that point would have been meaningful. In the other part of the problem, that is the second part of the problem, both point B and C becomes optimal. That is because one of the constant line, that 2x1 plus 3x2 equal to 16 and the objective function 4x1 plus 6x2 equal to 25, they have the same slope. So that means as the profit line moves, it becomes parallel to this portion, and because it becomes parallel, both B and C becomes optimal. Not only that, every point joining the line segment B and C also becomes optimal. All right, so that means point B is optimal and the solution is x1 equal to 0 and x2 equal to 16 by 3, z star is 57, and C is also optimal. That is the same C, x1 star equal to 17 by 4, x2 star equal to 5 by 2 and z star equal to 57. So the solution is for the first part and the second part has a common point C, and but from the second part we also have another point B, and therefore the entire line segment BC actually represents our solution space. That means there are alternate optimal solution, and any point between B and C we can actually take as our optimal solution, and we can work with that point. Is it all right? So that is how we see that this byproduct problem is unique in the sense that it has alternate optimal solution, and it also has a temporary degeneracy at a point D. All right. So this is exactly what is happening. Since points B and C are both optimal, all points on the line segment BC are optimal, which is a case of alternate optimal solution. Right. So thank you very much. And once again, this actually concludes our the four different cases that we have taken, special cases. However, there are other kind of special cases which we shall take up in the third lecture, which actually happens on different types of constraints and different types of variable types, that is greater than equal to 0, equal to 0, and less than equal to 0. So all those different special cases we shall take up in the next class. All right, in our next class we shall take up those kind of special cases. All right, so thank you very much.